Hello, everyone, and welcome back. My name is Corey, and you're my rubber ducks for the evening. And this is a series of episodes where we are creating a programming language from scratch using basic tools like Flex, Bison, Google Test, and ICU. And of course, we are writing this in a language. C++ is our language, and Vim is our editor. We're doing it all in a terminal window. And we are on episode number... What episode are we on? Episode 90. Okay. And this has been 100% live coding, which means you've seen all my mistakes, all my needs to refactor, and all that other fun stuff. Well, okay, so where does that put us today? Right now, yeah. Well, what I normally say, nothing up my sleeves. I don't have anything pre-prepared. We have been lately looking at optimization and trying to make our program run faster. And at the end of the last episode, if I say git log, the last commit was episode 89, right? So we're on 90 right now. So episode 89. But if I say git status, there's a few changes. And these are things that I did at the end of the last episode, but it was after my last commit. And I said, well, that'll be part of our first commit. But before we do it, we want to kind of, show what changes I'm doing. First of all, for the make file, in the make file, if I just say git diff on the make file on the left-hand side there, you'll see that the only difference is that I've set the optimization level to 3 rather than the standard debug with all of that stuff. So now optimization level 3. And I'm leaving it on that. But the other thing, okay, so we've got an untracked file. This is for just my call grind stuff. So that I can do some comparisons as I need to. And then we've got our this source program dash execute, and let's see what's there. Git diff source program dash execute. Okay, and there's only one character different, and that is I put an ampersand here before the word function. And all that I want to do is source program execute, and that is on line around, say 700. Yeah, right there. Okay, so I'm removing it. On the right hand side, that is, well, right behind me, I am going to start a fresh make, and so that we can compile this. In fact, forget doing it that way. Make test-j8. Just get a really fast compile going. The reason is I just want to show the difference in speed by adding that ampersand back. Okay, so first we'll get Notepad opened up here. Save a copy of it there. And if I say time./build apps tang-s means interpret as a script, and feed in our fibonacci.tang, we'll see that it's running in 0.79. I'll check the 0.791 because sometimes it's less, sometimes it's more, and just kind of save that off. And now I'm going to put the ampersand back and do make test-j8. I think it's only going to do one at a time just because. There we go. And running the time again several times. If I just choose this one, why not? And we can see that there is an improvement of about 4/10 of a second, 4/100th of a second. Sorry, evidently I don't know how numbers work. And that was just by adding this ampersand. Something else I'll do. WSL view docs HTML index. That way it's here when I need it. And I'll leave that there. And the other thing is make test watch. Okay. So what is this doing? Well, without the ampersand, what's happening is function becomes a copy of whatever's in stack of fp plus position, and then we pass that into the function. And these are all this is passed by reference, so it's not making a copy of it. But by putting the ampersand, we're saying, no, it's not a copy of it. It's the actual one. It's pointing to that one. So it's the same as if I had done this. Stack fp plus position. It's the exact same as if I had done that. Okay? By putting the ampersand, and it's faster to do that because we're not making a copy. So that makes me wonder, you know what? Look, I have the exact same thing here. Why didn't I think of that? I don't know. Oh, nope, this will probably fail. In fact, I even mentioned this the last time. Because we get a copy of it and then we remove it. Yeah. Told you it would fail. So, yeah, that's why we can't do a copy of it there. And it's possible that, you know what, the peek and poke might also here, just show that it's going to work. So when I call peek, push back, okay, so that's fine. Poke, okay, that's all perfectly fine. I kind of want to, if I were to go through and just look everywhere where the word stack is, and the problem is like, so for this one here, condition, it's stack back, but then we're immediately popping it. So, okay, I can't do anything about that. But jump if true, I'm not popping, so I could make that an ampersand. So jump if false, this one up here, same thing. Okay. Null val, let's see, there's that. Popping it. Okay, so can't do anything there. Popping it there. It's popped immediately. This one's popped immediately, and then we're pushing. Okay. These are probably all going to be the same. And of course, the main goal is to minimize the number of copies that are taking place. So for the equal, same thing. Not equal, probably the same thing. A lot there in the slice. But again, all of them are being removed. So get iterator. Yep. The casts are probably all the same. Call function, this one, yeah. And then we just did the call func I. Yeah, okay. So we did have one change. So we're just recompiling it, making sure everything passes. I don't think this will affect our time, but where did we change it? We changed it in the jump if false, jump if true. So that'll make our like loops and stuff go faster, slightly faster, very, very slightly faster. And on the right hand side, if we now run the time, I don't think it's really going to change that much. We're still in the same area. So that's fine. All right. So what do we want to do? We want to make this commit. Git status, git add source program execute, and now git commit and how about program execute optimization? For performance. There we go. Those are garbage collected values. Okay. Now, what do we want to do? Well, if we look at our fib, fibonacci.tang, so cat fib.tang, the function, we call this fib function a lot. And when we optimize the call func thing, well, we got some speed boost out of that. We want to do the same thing with the minus. Why? Because n is yeah, it's sorry, just it's something we can optimize. So so what all do we need to change? We're going to need to edit our source opcode no. First of all, our include opcode, our source opcode. We found that out last time that we forgot that. Our source for program analyze, our source for program dump, and our source for program execute. Okay, and then what is our source for AST node? Which ones are we doing? We're going to do the minus. AST node, is it sub? Binary. Oh boy. There's potentially going to be a lot of things here. And I'm going to go ahead and add the source for AST node, the one that we just did, function call, just so we have it. Now, if we look at the function call, or call func down here, call func I, we use I to indicate that we're using an index. We're about to do the same thing with subtract, except we're going to have it as subtract I and S. Because we're no longer going to have a subtract. Our current one is going to be subtract SS. And why these are just going to be possible improvements. So we will have S, S, I, and I, whoops, I. So this is stack and stack. This is index into the stack, top of the stack. Top of the stack, index into the stack, or index into the stack, index into the stack. And those are the four options. Now, yeah, we're looking at possibly doing this for all of them. We'll get there. First of all, it would be get RHS index, pop LHS, RHS equals stack RHS index. That is ugly. And I'm just saying it wrong. I'm saying RHS and it should be LHS. Okay, so I'm going to undo these changes. All right. Get index. that is going to be, this is going to be LHS is equal to stack LHS index. I think that is the easier way. And now this is going to be get RHS index. And now RHS is going to be equal to stack RHS index. Pop the left-hand side, push. All right. And then this last one is get LHS index, get RHS index. RHS is equal to stack RHS index. LHS is equal to stack LHS index, and then push that. Yeah. Huh. Is that how we want to do it? It would be better to have a direct jump than, I mean, I could just leave it as subtract, and then it has an extra opcode that says which pattern is it. Because this is going to be a lot of copy and pasted stuff. You know what? I'm going to go with this for the moment. And now, where's the subtract? There we go. That's stack, stack, and then index, stack, and then stack, index, and then index, index. Right? Stack, stack ends with index, index. Yeah. Subtract, stack, stack. Subtract, is it index stack? Index stack, stack index. You know it should go like that. Which means there. So stack index, index stack, index index. All right. So stack is fine. This is going to be a dump program check of 1. So is this, and this one's going to be a dump program check of 2. All right. Plus equals 2. Plus equals 2. And this is going to be plus equals 3. SS, SI, IS, II. Didn't mean to quit. Nope. There. Now we're on the dump bytecode. So here's a subtract. All right, so the first one is going to be SS, SI, IS, II. Okay. This is going to be PC plus equals 2. There, I think we've got it all figured out almost. Then yeah. Except this is now going to need SS, SI, IS, II. All right. I know I'm not done with this. So in the execute, this is going to be ugly. I'm just trying to get through it. This is going to be SS, SI, IS, II. Okay. So SS has a stack check of 1. SI has, or 2. SI has a stack check of 1. This has a stack check of 1. And then this has doesn't have any stack check here. I'm leaving that there just for the moment. So in this case, the right-hand side auto RHS index is equal to bytecode of PC plus 1. And now this is going to be auto ampersand, because we learned that, of stack FP plus RHS index. But in order to do that, RHS index needs to be there. Is that right? I think so. Don't pop it off. Okay. RHS index. Okay. Because if it's A plus A, well, that's a different thing altogether. Okay. Push back left-hand side minus right-hand side. Okay. That should actually all be correct. But where is the execute program check? There we go. We need that. So SS doesn't need the execute program check, but this does. And that is there. And this one is going to be 2. So now let's do this one, the IS. So that's SI. IS is going to be, the right-hand side is popping the back. The left-hand side, LHS index is equal to this PC plus 1 is equal to LHS index. Okay. No, should be FP plus. I don't need to pop that. I just now need to push. Okay. Now, all of them. I think that is right. So we get the right-hand side. No, okay, wait. The left-hand side should go first anyway. So we'll, that's PC plus 1. This is going to be PC plus 2. That's why execute program check is 2. Yeah. And then these are, that's a 3. Okay, I think that is all of them. And now we just don't know how to do the subtract. All right. So this is compile the left-hand side and right-hand side. But if it equals subtract, I no longer want to do this. So I'm going to say if this op equals opcode subtract something, then do that. Else what happens after that break? Nothing. So I can return. Okay. Why do I have this op? This op, what is this op? It's operation. There we go. And our classes of AST node binary. Operation is just an enum. So it's operation : subtract. Okay. All right. So if it does, then do something different. What is the something different? Well, I'm glad you asked. We have to figure out, let's just look at this for the left-hand side and the right-hand side. So if the type ID of this arrow LHS is equal to the type ID of AST node identifier, like I said, this is just going to be ugly. Is it going to want an ampersand there? I think so. The LHS and RHS, what are these? What's the type? AST node binary. Those are shared pointers. Okay. So I need to dereference them. So they're both identifiers. Then what do? Program.add bytecode, uinteger t, subtract II. Okay. Not a uinteger t, but something. How did I do it here? I say, give me the identifiers. Okay. All right, I don't need LHS conv. There we go. I think I'm going to say an integer t, and we'll say this as LHS index -1 RHS index of -1, and I'm going to use these. If that, then LHS index is equal to identifier dot at name. Okay. Why am I doing it like this? Because I need to do this check several times. And now I'm just trying to okay, so this is going to be you know what? Just change this to name. Name. Okay. And this can also be name. And this will be RHS. All right. Now, I've got to have 4 cases. If the LHS index is greater than or equal to 0. If RHS index is greater than or equal to 0, then that means I've got this case right here. left-hand side. So here, that means the right-hand side is not 0, but the left-hand side is. So the right-hand side needs to be compiled. Okay. And then subtract. The left-hand side is an index, and then this is a stack. Okay. All right. Else. So the left-hand side index doesn't exist. So we'll say if RHS index is greater than or equal to 0, then right-hand side, this needs to be left-hand side. This is going to be the SI, and then the right-hand side index else. Which one gets compiled first? Scroll down. Left-hand side. And then right-hand side. And then subtract SS. All right, so this is what we'll need to simplify to work with any of these. But for right now, we'll just see if this works. Oh, line 46. Wait. Binary.cpp. Oh. Oh, it's subtract. Not all caps. And I probably did that intentionally, now that I think about it. ST-node identifier, I need to pound include this. And remind me to add that to the make file. all of the tests pass. Okay. And right now, AST node binary. And that is declared before AST node binary. Okay, good. Wait, why is it twice? AST node identifier. There. Anywhere else? Ranged 4, that makes sense. All right. Now, the first one was the lowest time that we've seen. If I look here, 756, so sometimes it looks like it's taking longer, sometimes it's less. I think it's just a very small change. And binary compile, not the compile, I want to go to the execute. And all I want to do is I want to just want to see which ones are being executed. So if I go back to the make test, did I mess up my make file? Possibly. Actually, I think I know what I might have messed up. There, needed a slash at the end of that. Okay. Try this again, shall we? And again, this isn't about performance. This is about, are we using all of these opcodes that we're writing? Only using 0. Only using subtract SS. And in fact, if I do it with So the subtract SS is the default one, and that one, yeah, that's why we're not seeing a speed boost, because we haven't done anything. All right. Where do we need to go? In our node binary, that's number 6. Because I forgot my asterisk there. That is why. Somebody popped into the chat there, said hi. Hello. Let's go back to our compile. Okay. 0 and 2, and if I run this, those are all using 2s. Those are IS. Why is that the only one? Well, no, it makes sense for this one. There's going to be a lot of them. I'm not going to scroll all the way through. Let's just rerun our compile. That's the speed up I was looking for. There we go. I'll just choose this one because that's what I've been doing. That is the speed up. So going from almost 0.8 down to 0.73. Very much better. Okay. So now the question is why aren't these other cases being used? Let's put this back on our compile that watches for changes. Let's edit our test and just look for the minus sign. Oh, that's not going to be. How about we look for the word subtract? Okay, so all of these are going to be SS's, so that makes sense. Those are all SS's. Yeah. I don't think that until we get into variables. Well, these are strings. I bet I don't have an A minus B anywhere. See, I'll have things like A is equal to A plus, blah, blah, blah. Is equal to A plus 1. Yeah, so I bet I don't have one. I don't have a test for that. That's our compiled function. Native functions general. Compiling the template, compiling the shortcodes, the library, use. You know what? Let's just create a new one. Test, and it's going to be optimization. Subtract. And now I just need to say auto p1 is equal to Tang compile script. What do I want the script to look like? Let's say A is equal to 1, B is equal to 2, print A minus B. I expect that to be something. Okay. And now let's make a couple copies of this. 2, 3, 4. All right, so for A is equal to 1, B is equal to 2, A minus B should be, of course, negative 1. Easy enough. But if I want A minus 5, what would that make it? Well, negative 4, but that is index stack variable. Here we'll have 5 minus A, and that will be stack index. That, of course, should be 4. And that's going to be stack stack. And, of course, that answer should be 5. The point is to make sure that there's a 0, 0, 1, or 1, 2, 3, 4, whichever numbers I chose. All 4 numbers at the very end of this, at the very end of the test. Yep, 3, 2, 1, 0. So I hit every use case, and we are passing them all. Okay, that is fine. That's what I wanted. Now let's go back to the execute and remove our couts. and do an initial commit of this. I know that the stuff isn't pretty, but we'll get it there. Okay, what are all of my differences? My make file, I'm going to ignore that no, I can't. Should we start working with optimization 3 and only change it when we don't need that? Maybe that's a valid change to make. Identifier, these are the 4 new opcodes. Node identifier. Yep, all that looks correct. I can well, should I remove this subtract? No, not yet. I may not be done. Subtract. Okay. The make file, the include opcode, source. Actually, everything in source. Do I want to add the tests? Yeah. That might not be the best way of testing it, but I think I have an idea of how we can test it. Okay. Add 4, subtract opcodes for performance. Okay. For stack optimization. That's a better wording. All right. Now, how can this be better? I am the first to admit that this is ugly. But it's faster. So let's see what we can do first with the... Because we know we can do another one. We know we can do less than and get another speed boost. So let's focus on that really quickly. So less than... Wait, it is less than, isn't it? Catfib.tang. Yeah, it's less than. So we need a less than SS, a less than SI, a less than IS, and a less than II. I don't want to... I don't want to update all of these, all of the comments yet. We'll worry about that. Okay, so less than. Okay. SS, SI, IS, II. Oops. There. 2, 2, and then this is 3. All right. Next. Huh. So I think we're just going to SS. So for these subtracts, yeah, you're probably wondering why I just stopped talking. Because I realized I can do this. I can say an opcode, and then u integer t LHS u integer t RHS. That's fine. Oh. I had to pass in the out. This is not pretty. ostream ampersand out there. Out the opcode. You know what? It's probably better to just say, have this as a pound define dump binary SS. Dump binary SS, and then dump binary really, is it SS? No, that's, it should be II. This is with a single one. PC plus 1. This should have been plus 2. So that was probably a mistake earlier. And then dump binary by itself is going to be so dump binary I, dump binary II. I'm trying to decide if I want to add anything else to that, and I think the quick answer is no. So this can be well, plus plus PC. I think I'll leave the break. I always want to see the break. This can be PC plus equals 2. And this can be PC plus equals 3. Okay, so dump binary 1, dump binary 2. Dump binary. That should only be a 1. Again, just trying to streamline it all. All right. That's a lot better. So now if we go with the, where's the less than? That's these right here. And these are going to be SS, SI, IS, II. All right. Those should all work now. What about executing them? So I think I'm going to yank from there down to 42. Because just about everything is the same except for the stack push back. So did I just mess that up? Nope. Okay. So I'm going to pound define something called binary op. And it's going to be that, followed by that, followed by... Which one is this? This would be SS. I'll add the SS. And then just not put those things there. Let's get all these fixed. The next one is II. All right. And now you know what? I'm going to leave in the PC. What was it here? PC plus plus PC? Yeah, it was. So it's binary op, and then whatever kind it's supposed to be. Yeah. All right, now let's get all this fixed up. That's all we need to do. Did I just do that wrong? Did I paste it in twice? SSSIISII. And then did I just mess up? Well, that's what Git's for. It'll tell me this in a moment. So my subtract is those four things. I'm going to go back up to the top and make sure that it makes sense now. SS, pulling them both from the stack. That's fine. SI is right hand side from the index, left hand side from the stack. IS is right hand side from the stack, left hand side from the index, and II is left hand side from the index, right hand side from the index. Yeah, that all looks correct. Okay. Now the less than. See if this works. Oh, I need to tell it to compile, don't I? Oh, I need to say for how the compile should work. Yeah. That makes sense. So in fact, so the subtract is there. That goes all the way down to there, so 40. Define binary op op. No, I don't need that one. But now how do I make that op a drop-in replacement for the word subtract, for example? I think it is a macro. Yes, yes, yes. I just don't remember. I'm pretty sure that there is a way of doing it. If not, well, Well, these are directives, but concatenates two arguments. Yeah. Put 2 pounds in between them, I think. So if that's the case, let's do this as op. There. Oh, wait. I don't think it'll let me do that. I was going to say op, pound, pound. Yeah, I don't think it'll let me do that. Two arguments. Yeah. Well, you know what? Okay. If this doesn't work, we can always undo it. So it's just binary op and then op. All right, now. Yeah, it doesn't give the... I hate these articles. I just want to see I'm wondering if I can just cheat. Specifically, if I do this. Pound define II as there. So does the underscore mean something special here? That's not what I wanted. I'm not seeing it. You know what? I got to get this done. So let's do the right order. SS IS, no, SI IS II. And yes, this is going to be ugly, but I don't care. It's just at this point, just want it to work. All right, now SS, SI, IS, II. Where is this? Oh, in the dump bytecode. We're getting there. We're getting there. At least I think we are. Yeah, that's not good. So let it recompile again, and at the same time, let's see. It doesn't look like there's any files that I have not saved. So I can go ahead and say that this subtract should go right there. And this less than should go right there. Ooh. Nope. Can't do that yet. I will go ahead and leave those there. Now, if this still gives me an error, then that probably means that unaligned. Okay, so let's figure out where that is. We want to run using GDB build apps test. Just run it, and it's in the while backtrace. Make an integer. Oh, it's in the add. In the add. Tcache get when we're calling the operator new in garbage collected HPP 22 in add so whatever I'm putting in there we can figure it out really quick. Which one is the... So in test 1178, we've got a less than. Did that corrupt what we're getting? Okay, so I want to see out p1 dot dump bytecode and just see what it says. Okay. All right, so we've got a null val. I'm assuming that's our A and then our B. Integer 1 is being poked into 0. We're going to pop that. Integer 10. And then we're saying index 0 and then whatever's on top of the stack. Okay. That seems right. Now, if we run the GDB of it and get the backtrace, it's not happening until we get to the add. That's weird. We'll come back to that. I want to see the diff. Did I accidentally change something? So we've got our less than SS, SI, IS, II. Okay. Pound define binary op, which worked with subtraction. II, IS, SI, SS. So is that the opposite order? I think so. SS, SI, IS, II. SS, SI, IS, II. So I maintain the right order. And this is with subtract. Else, less than, it's using LT. SS, SI, IS, II. Okay. Opcode, I added those. SS, SI, IS, II. SS, SI, IS, II. 2, 2, and 3. Okay. Binary. Dump binary 2. So that's +2, +3. That's fine. Binary SS is two, 2, and 3 on the increment. This is +2, +1, 1. So, it's weird that it's happening on the add. op II. Oh look, that should be SI. That should be IS. That should be II. SS, SI, IS, and II. So it's in my execute. Okay. SS, S, I, IS, II. Go back down to the less thans. Oh, there they are. Whoops. SS, SI, IS, II. Rerun this. All tests are passing. That's good. All right, and sorry, stop to think happens, you know. Go back to test, remove that, where is that C out? There it is. All right, and now I want to see this. Where's the time? Look at that. Low numbers. So starting off at 791 down to 715, that's 10% over the course of a couple things. That's pretty good. Let's see. So we want to wrap this up. And I'm going to go back to opcode.hpp. All possible opcodes. suffixed. That an index is provided during execution. The SI order in the bytecode indicates the of the associated values. For example, not pop, let's just say add SS I think that's good enough. Okay, so now I don't have to do, so for the left hand side, instead of pop this, do that, push, we'll just say that. And this is now going to be push. There. That cleans that up. As usual, on the right hand side, I will do a make clean, make tests, and while on the left hand side, let's do our get stuff. So get diff, yeah. opcodes for subtract and LT. Make sure all my tests compile right, pass before I do this. And they are. All right, make our docs. For this, what episode are we on? Episode 90. Okay. And now that we've done this, if we happen to look here, where would that be? Opcode? Yeah, a file list include oh boy. Everybody needs this. Of course, we know that. Our enumerations, there we go. If we go to more, for SI, blah, 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 we'll see that subtract and less than are there. Very happy for that. Okay. Get push episode 90 up. Yay. All right. And last but not least, just a quick little overview of where our source code is. 11,700 lines of code. And I like the change, though. I like the direction we're going. It's going to allow us to be able to add these variations without having to add a lot of boilerplate. That's the whole reason for adding the macros. Yeah, we're going to have to just do more of it, I guess. But this puts us in a good spot. So we now know that over the course of these last 1 or 2 episodes where we focused on can we improve the efficiency, the answer is yes. We've gotten about a 10% increase in efficiency. And now we know that we can do that with a lot more. All of our math, so addition, subtraction, multiplication, division, modulo, all of our comparisons, less than, equal, greater than. No, not greater than, sorry. Less than, equal, not equal? Well, not. Our indexing we could add it to. Our slicing we could add it to. Now that's going to be difficult because slicing gets 3 values. Yeah, that's going to be messy. Okay. We'll think about the slicing. But, again, the best part is we are improving. And I've been mulling over the whole garbage collected and how that works. And ultimately, garbage collected has to call new a lot. And we use a singleton object pool, which maybe that's not the best way. It's possible that's not the best way. I'm going over that in my mind because I mean I think we saw that we called what was that the mutex, right? Was it 29 million times, something like that? It's a big number, and it's like, yeah, that's taken up a bit of time. So if we could eliminate that and just have a better structure. Maybe the problem is why do we feel like we need it? We don't need it for integers. We might need it for strings. Strings are a big part of this, but we need it for vectors, for maps, but we don't need it for numbers, so or true false. Got to think about it. Maybe there's a better way, more efficient way. I would love to get this down to less than half a second, or maybe more. Just we'll work on it, and to get our 4 milliseconds here maybe down to 2 milliseconds, that would be awesome. But for right now, we have ended up in a good place, and we'll call it for the night. Thank you for joining me. Have a great day, and I'll see you later. Bye.